Today we're going to talk about the camera model again. We have covered the basics of how do the cameras work. We have talked about the physical principles behind their functioning, and now we're going to dive deeper into the physical principles of the image formation itself. So I'm talking about the way in which the objects in 3D space are being projected onto the photosensitive matrix. We're going to briefly cover what's going on with the human eye. We are basically trying to recreate the human eye in some sense, in one way or another, and we have to care about the most important parts of the eye itself. So as we know, it doesn't have any additional lighting. It's a passive sensor, and the light is entering the human eye via the pupil. So after that, the light goes through the lens, and the same stuff is basically going on in the cameras. And the photosensitive matrix here is called the retina, and in our eyes it is curved. In regular digital cameras it is not curved, but the whole scheme is basically the same. The simplest way of recreating this camera is the one that you have probably already heard about. It's the pinhole camera. So you can do it with a shoebox or actually any other box, or with a wall with a small hole in it. So the pinhole camera itself is the right part of this box in the image, and the functioning of this camera relies on the beams of light or rays of light going through this little hole, and this pinhole camera forms an reverted image of the whole scene on the photosensitive matrix or on the wall behind this small hole. In reality, the optics in digital cameras is much more complex, and it's not just a small hole and that's it. The point here is that we would like to increase the optical flow that goes through the camera. We would often want to adjust the field of view, or we would like to capture objects only on a certain depth in the scene. So there are multiple optical tools to do that, and we have to deal with the aberrations that are caused by different refraction coefficient for different wavelengths. But we will not cover that much. We just have to remember that in the grand scheme of things, the lenses are a big part of the digital camera, and we have to take care of them. We have to understand how to make corrections for their performance, because they are, of course, not ideal. And they are not only not just a hole in the wall, they are even not a thin lens. You know, from the school course of optics, you know the model of a thin lens, and the lenses are really not thin, they are thick lenses. And there are various effects like interference, diffraction, and so on. And they are all happening, and the real models of the lenses are much more complex than that. We will talk about the camera calibration in that regard. Let us take a look at the overview of the model of the pinhole camera that is used in OpenCV library. On the right here, you can see the drawing that we have already seen in the previous lecture. And the big blue arrow over here on the right is the object that we are trying to capture. It is described by 3 coordinates, x, y, z, with the subscript of W. And this W means world. So this object belongs to the world in 3D space, in meters as you see it. Further to the right, there is a smaller arrow, blue as well, and it's the image of this object that is in the surface of the photosensitive matrix. So it is characterized by two values by u and v. And it's a planar point. Here we are working with the pixels, with pixel values. Those ones that we can find out with some pipeline of computer vision that we were doing before. When we have found some object, it is usually described by just two numbers, x and y, middle of the bounding box or something like that. Further to the right, we can see these three black arrows, and their intersection is the focal point of the resultant optical system. What do I mean by that? Well, by that I mean that we do not care about each individual lens in the optical system. We are just interested in one virtual effective lens that we can work with. And the focal point of this effective lens is denoted here as the intersection of three big black arrows. In the middle of the matrix, you can see the principal point. It's basically the center of the optical system, or it's the point where the light beam that is going out of the focal point, where it ends up if it's normal perpendicular to the photosensitive matrix. It's the main optical axis intersecting the image plane. The coordinates of this principal point are c sub x, c sub y. We will see those two later. Another two characteristics are the focal lengths, and I'm talking about them as there are multiple of them. Well, in reality, there are two of them, and we'll cover them as well later. So let's check the formulas on the left. At first, you can see that we have a vector of xc, yc, zc, and these are the coordinates of the object in the camera frame, not in the world frame, but in the camera frame. And the coordinates of the object are brought to this reference frame with the rotation translation matrix in homogeneous coordinates. We have our vector x sub w and so on, and we rotate and translate it so that now it is in the reference frame of the camera. After that, we are performing the operations that are given on the left bottom of the slide. We are taking into account the principal point, and we are also taking into account the focal length of the camera. And also we are normalizing the coordinates by dividing by z, c. Those are the formulas that give us the point where the image of the object belongs to after we have performed all those trigonometry and geometrical operations of projecting or imaging, as it is usually called. So let's proceed to the same image, but with a stress on the so-called intrinsic parameters of the camera. We have talked about cx and c sub y. Those are the coordinates of the principal point on the matrix. And also we have fx, fy. What are those? Well, those are the distance from the principal point to the point where the focus is. So it's the focal length that is measured in the pixel units. You can go along the x and y axis in the image, but also you can use the same units to go in a perpendicular direction, so you can measure the distance to the focal point. That is what fx is, basically. So fx and fy are the coordinates of the focal point measured from the principal point in the units of x pixels and y pixels. Why could they be different, you might ask? Well, the thing is that, first of all, the optical system itself is not ideal, and it is not always perfectly aligned, so the effective size of the pixels could be different because of that. And in order for all the calculations to be more precise, we have to consider those two values separately. If we imagine that we have all those 4 parameters already calculated, or we know them from the model of the camera somehow, we can perform the operation that is given at the left bottom of the slide over here. So this vector xc, yc, zc is the vector of 3-dimensional coordinates of the object in the camera frame. And with multiplying them by this matrix of intrinsic camera parameters, we end up with the vector in homogeneous coordinates, where the third coordinate is always 1 and we can discard it, and u and v are the coordinates of the object basically in the image. That's it. So this is the main part of the whole imaging process. This is the imaging procedure itself. And here we need only those 4 values, and fx and fy are usually close to each other, and the cx, cy are usually close to the center of the matrix. We will see that later in the seminar when we are going to calibrate the camera. But yep, we need them, and without knowing these values, we cannot really recreate how will the camera work. Here we can dive just a bit into the details of the application of this rotation translation matrix. We can represent the rotation, as you know, by a 3x3 matrix in 3-dimensional space. And the translation could be represented by a single vector 3x1. And so-called homogeneous coordinates make it possible to accommodate all of that into one single matrix, so that bringing some vector into another reference frame works by just multiplying this vector by a single matrix. That is very handy, useful, and convenient. So you can multiply those matrices, you can use them instead of just 2 vector operations, first rotating and then translating. You can use just one single operation of multiplication, and it is in reality equivalent to the regular form of doing the same thing. You can check the matrix operations by yourself. It's the same as applying a linear operator to a 3-dimensional vector. And the cost of that is that we have to carry with us the 4th fake, so to say, coordinate that is never changing. It's always 1. And this form of representing vectors and operations with them is called homogeneous, because we don't really divide the operations that we perform over vectors into rotation and translation. They are embedded in the same matrix. Just once again, the whole thing that is going on here is we see the ball or any other object, and with the ball we usually consider its upper middle point of the bounding box to be the position of the ball in the frame. The physics around us goes along these matrix operations, so that we get the u and v coordinates after the camera has performed its operations over the light beams that travel from the ball through the optical system onto the photosensitive matrix. And yeah, basically that's it. So then we're reading these values from the photosensitive matrix, and we can process it with all of the instruments of computer vision that we have talked about previously. So just once again, what's going on? The bottom formula here is the bringing of the position of the ball in 3D space in the world reference frame into the camera reference frame. And at the upper part over here is the procedure of imaging through the optical system, through the specific camera, of this 3D vector into a 2-dimensional vector of just 2 coordinates, x and y, that we have inside our frame. We have briefly talked, I just mentioned it, the fact that the optical system is not perfect. We have talked just a bit about the lenses in the optical system being not perfect, not precise, or just not thin lenses. Okay, so the thick lenses introduce various types of distortions. And those distortions are already familiar to you, that's for sure. You can easily recognize the image that was taken by some GoPro camera or a fisheye camera in your phone, and that is what basically going on there. So there is a strangely warped field of view, and the objects on the sides appear to be strange. That is called barrel distortion. And the thing is that just the optics of the materials that we use work this way, and beams of light that enter the optical system from different angles are transferred in a different way to the photosensitive matrix. That's basically it. OpenCV has a complete enough model of these different distortions, and the way of finding out these K1, K2, K3 parameters over here is the calibration. So we will have to wave with a chessboard pattern near the camera during the seminar, and we will get those values for the specific camera itself. We have to calibrate the optical system or the camera of each robot individually, because those lenses are slightly different and the cameras itself are mounted in the head of the robot slightly differently. So if we change the lens, if we even adjust it, even just randomly, or if the robot have fallen onto the ground, we will have to readjust the optical system by calibrating it once more. This whole procedure is about getting those parameters. Also these parameters as well, because this cushion or barrel distortion is not the only thing that could be off in the optical system. Another thing is that the matrix, the photosensitive matrix or the sensor, could be misaligned and inclined in relation to the lens. That is called tangential distortion, and it is described by some more parameters that could be identified with the same procedure as the parameters of the radial distortion during the calibration of the camera matrix. We will not dive into the mathematics over here. You'll just have to remember that the parameters of the distortion or the parameters of the calibration of optical systems could be different, even for the cameras that appear to be same, or they could even shift if the camera is readjusting itself, if it has an autofocus. So we have to remember about the distortion. The general case of the distortion model that is used in OpenCV is the following. So in some modes of calibration, we can find out the values of all of the parameters here. Usually we don't really need that, because some of those parameters are often small. And since the cameras are usually kind of good enough, we can omit some of them and take care only of the 5 main parameters that we will take a look at during the seminar. The default way of calibrating the camera is without specifying the additional parameters that are here on the right. Most probably we will not need them initially. In the seminar, when we are going to calibrate the camera, we will do it in the, so to say, minimalistic manner. So what we will do there is we're going to take a chessboard pattern, almost the same as here, and I'm going to wave it all over the place near the camera, and we will take some pictures. Well, we will not take 40 pictures, that will be too boring, but we will take, I don't know, 10, 15, something like that. And after that we will run the calibration procedure, and we will obtain all those parameters of the optical system distortion, as long as the fx, fy, cx, cy, the intrinsic camera parameters, those ones. And after we have found out the exact values of these distortion coefficients, we can perform the unwarping. So if you have a fisheye camera and you're not satisfied with straight lines curving all over the place and people bending at the side of the frame, you can perform the undistortion procedure. What's undistortion? Well, that's pretty much clear from the image over here, you can see that the curved edges are becoming straight as usual and as it's intuitive to your geometrical perception of the world, because you see the straight lines as straight, usually. It's possible to do that given the values of the distortion coefficients. Now let's talk about the main thing here. Why do we even need that? Basically, we need the geometry of the camera or the geometry of the image formation because we are interested in the world positions or world coordinates of the objects. It's cool that we have found out that the ball is somewhere in the bounding box. That's good. But we are mostly interested in the world coordinates that are measured in meters because we want the robot to, let's say, approach the ball and kick it. Knowing how exactly does the image formation works allows us to perform some procedures more or less in the backward order so that given the pixel coordinates of the objects, we can find out their real geometrical coordinates in the scene that we are filming. The simplest way to do something with the real world or real objects or real sizes is to measure the size of the object with the camera. We don't need any plane model, the surface model or anything like that, or inclination angles that we will cover later. It's just the simple procedure of measuring the distance with a single eye. So imagine that you have an object of some unit size, let's say 5 centimeters. Clearly you can measure the distance to this object using just the visual size of this object in the frame. And here we can even omit the knowledge about the camera calibration. So using this approximate model of the sine, well, yeah, it's imprecise, but still it works quite well for rather big distances. We can establish that the height of the object, which is denoted in the slide by h, it's almost equal, let's say, to the height of the object multiplied by the angle by which we see this object in the frame. This multiplication of distance and angle stays the same for different distances and different angles. This is a constant, and if we have once found out the value of this constant, we can use it to revert this formula back, and we can measure the distance knowing the height of the object. And it could be even not the real height in centimeters, it could be just the height in pixels, because in our approximation, it works more or less the same. The idea here, and we're going to implement that with the real camera, is to measure the distance to a unit object, judging by its size. That's it. The next thing that we're going to talk about is the pic-to-R or picture-to-real problem. This is the fundamental thing that is basically the punchline of the whole lecture, and the problem is already familiar. So we know the height of the robot, we know the inclination angle of its camera, and we know how it's rotated, what the position of the robot is from the localization. We obviously need that. And we have detected a ball somewhere. So we are interested in solving the problem of finding the real world coordinates of the object, given all those parameters and the coordinates of the ball. That's what we are trying to do. Here we have almost the same scheme and a bit of trigonometry. So you can pause the video and try to derive this yourself. What we are interested in is the distance y wave sub w. This is the distance from the robot, or it's better to say from the projection of the camera on the surface, to the ball. Just for clarity, the x-axis of the robot goes to the right. Let's imagine that I'm a robot, so x-axis is to the right, y-axis is straight, and z-axis is to the ceiling. So here, first of all, we are going to calculate the distance along the y-axis. How can we do that? Well, we can check this scheme, and the angle psi, if we will be able to calculate it, will allow us to find out this y hat sub w from the height of the robot. The height of the robot is known, it's specified, so the only thing that is missing is the angle. Okay, Let's go further. First of all, the angle beta is known to us already because that's the inclination angle of the head. We can calculate that from the kinematics of the robot. We can add the pitch angles in the hips, in the knees, in the neck, and so on, and we can sum it all up, and we will find out the angle of inclination of the optical axis. The next thing that we need to find is the gamma angle, and the gamma angle is being calculated from the model of the camera. Let's take a look at the right part of the slide, the right side of the slide. So this angle gamma is calculated by subtracting the c sub y from the coordinate of the ball, and then dividing that by the focal distance measured in the units of the y-axis. So this is the angle of deviation of the ball from the optical axis. That's it. Then we take the arctangent of that, and we basically have the angle. After that, there is nothing that much complex, so we're calculating the xi angle. It's pi over 2 minus those two angles that you can see in the scheme. And then we are calculating the y wave sub w by multiplying the height of the robot by the tangent of xi. Or if we just move it all around, it will be cotangent of the same angle, but pi over 2 minus xi. That's it. And this whole procedure gives us the distance from the robot to the line where the ball belongs. After that, we have to deal with the x coordinate, but that will be simpler. Well, here I think it's better to pause the video if something is not clear, and you can try to do the math yourself, because it's kind of fundamental. So do that, and if it's all good, let's go further. Here we're looking at the scene from the right, and in the next slide we're going to look at this whole scene from the top. So x is to the right, y is straight, and we have already calculated the y sub w, which is the distance from the position of the robot to the line where the ball is lying on the floor. Here, basically the same thing is going on with the world model. We're subtracting the coordinate of the center of the photosensitive matrix from the x coordinate. That gives us, dividing this whole thing by f sub x, the tangent of the angle. Basically, these two triangles, this small one over here, that is measured in pixel units, and this one that is bigger, they are proportional. That, with the basic ratios, gives us the x sub w coordinate, and we're happy because we have calculated the real-world positions of the object that is lying on the floor. For robotic football, for our league, that is enough because the balls do not really float around yet. Later, well, maybe in 10 years or something, we will have to transfer our vision to that, to the stereoscopic vision. But for now, that's not necessary, and the rest of the league is basically working with this scheme of calculating the position of the ball. We are using the scene geometry. We know in advance that the ball is on the floor, and that's why we can calculate the positions. That gives us a determinate system of equations, basically. From the camera model, we get one equation that is describing the beam of the light, and the second equation is the equation of the surface, the horizontal surface. And all the trigonometry that we're doing here is the way to solve the system of equations just visually and simpler than in general case. And it all just makes sense because we were using some geometrical considerations. The last thing that we need to do is we have to take into account this rotation of, or not this rotation, but this rotation, just the rotation of the head. The rotation of the head is given by the angle alpha. So here R sub alpha is the matrix of planar two-dimensional rotation by this angle. We perform all those operations with calculating x and y without this angle, and then we just multiply this two-dimensional vector by the matrix of rotation, and after that we get the whole complete peak to R procedure with the coordinates of the object in the robot's frame. After that we can do whatever we want. We can plan the trajectory or kick the ball if it's near the foot already. So that's the story about trying to find out the world coordinates of the objects given the geometrical model and the positions of the object in the frame. That's it for the lecture. Thank you.